neural network. This is a feed-forward neural network that has a one-pass training. So it's quite fast network. So just a single pass training, and this particular network was first proposed by Donald Specht, and that is found to be a 3-layer feed-forward network with a one-pass training mechanism. And the PNN is primarily considered for classification and the mapping purposes. PNN is found to be very effective in all types of speech processing domains. So a class of pattern recognition and classification tasks, speech processing, are dealt with by this PNN. The PNN is based on statistical principles derived from the Bayesian decision strategy and non-parametric kernel-based estimators of PDFs, probability density functions. So PDF will primarily have a Bayesian decision-making strategy and will use a non-parametric Gaussian kernel. So there is the basic structure of the PNN. The first will be the pattern feed layer. Now in this pattern feed layer, there will be a layer of connectionist weight. Then comes a middle layer of the pattern layer. So a mid layer that will deal with the patterns. This particular layer will primarily cluster the class-wise patterns, class A, class B, class C, like that, class M. Then there shall be one more layer that is called a summation layer. This particular summation layer will try to sum up the class conditional densities. So since the decision making is based on the Bayesian conditional probability, so the class conditional densities of the classes of the different classes due to the pattern vector capital X shall be here summed up. Here those will be those will be clustered and grouped, and then finally there shall be a post priori decision making process starting, where from there the probabilities of the classes, the maximum class probability of the classes shall be calculated or shall be found, or a grouping based on the maximum class probability will take place, and then the summation, then the last part where there shall be a further class-wise summation leading to the decision making. So here the benefit that the PNN shows is that it guarantees to come closer to the Bayesian optimal decision, provided that the class PDFs are smooth and continuous. So here we should remember that the PNN finds the probability density functions of the features of each class from the provided training samples using the Gaussian kernel. So since this is a one class or a one-step training, so in that one-step training, the priority is to find out the class-wise maximal conditional density functions. Those are grouped and then placed in the class-wise clusters. So Now in this further, we need to remember that the PNN is based on the Parsons window decision making. The Parsons window method is a non-parametric recognition procedure that synthesizes a calculation of a PDF function by superposition of a uh, uh, number of windows, replicas of a function g that is called a kernel, or g or f, that g that can be written like this. So this is a kernel function g, where it takes a vector x, and that particular vector will be a prototype vector that will find a difference, or will find a distance measure uh, compared to a vector small x of L, and that comes from the sample space. And this particular function, called the kernel function, will do this for all the values, uh, for all the samples. Then finally will generate a function small f of x, where this x is a dummy argument for a point in the sample space. Small xl forms the training set, and lambda is a function such that limit of lambda for all n, for large n tends to 0, and limit of n, when it is scaled by infinity, will reach an infinite value. So this particular Parsons window technique is crucial for the for the for the working of the PNN. Now this particular calculation is consistent in the quadratic mean, where we take a limit of the estimation of the value of the function small f of x minus small f of n of x square, where small f of x is continuous. Here, consistency means that this particular simple approximation is a well-behaved method or function, such that when the number of training samples grow, the estimate tends smoothly to correct the density. Now the Bayesian decision criteria is the optimal classification procedure if the PDFs of the classes to be discriminated prior densities are known. Now, this is the particular Bayesian procedure that can be considered for doing the classification, where C is the class level that is generated by the classifier, and small x shall be the vector in the sample space, and small f of kx is the density of the kth class, and the coefficient gamma contains the prior probability and the risk coefficient, if there are, and which is linked to a particular class. And that can be the complete summarized topology of the PNN, that has four primary layers. One is the input layer, next is the hidden layer, next is the summation layer, and finally the output layer. So the sample feed takes place in this particular layer. So in the input layer, the sample feeding will take place. So these will be all connected by the connectionist weights. Here there will be some sort of gradient descent taking place. So in this particular layer, in the layer between the input layer and the hidden layer, there will be some form of gradient descent taking place, and that particular gradient descent based training shall generate the class wise conditional probability that will be fed to the hidden layer. Then that one shall be passed on to the pattern cluster layer. Now this particular pattern cluster layer works together with the summation layer, and there in the summation layer all the conditional probability density values coming from the hidden layer shall be grouped, and a summation value will be generated. So the decision that shall be derived is based on the fact that the feeds that have high probability of decision in favor of a class will decide the particular class. So here the class probability values, the class conditional probability values of all the neurons are calculated. That will be summed, and then in that summation block, if the class conditional probability value for a particular class is favored, so the decision shall be considered in favor of that particular class. So that is how the PNN functions. Now that can be shown to be in a different form by considering that PNN to be formed by several subnetworks, and by considering that each of these subnetworks is a Parsons window PDF estimator for the classes. So the input nodes are the set of the samples that are taken from the sample space. The second layer consists of the Gaussian functions that are formed by considering all the given data points to be the centers. The third layer performs an average processing of the responses generated from the second layer for the classes. The fourth layer performs a vote, selecting the largest value, and then fixing it in favor of a particular class. Then the associated class level will permit in generating the decision. So by considering the Parsons window and sub network perspective, the PNN's processing and discrimination can be seen from a different dimension. Now PNN since relies on the calculation of class conditional probabilities. Therefore, in the pattern or feed and the middle layer, these class conditional probability calculations take place. Then a type of voting will take place. The type of voting that favors a particular class will lead to the decision. So the Lth pattern unit computes its values like this. ZL is equal to small x of L multiplied by W, and y of L is a function of G of ZL, where ZL is the net input of the Lth pattern, and YL is the output. Small xl shall be the Lth pattern vector. W is the shall be the scaling weight, and the activation function G of X shall be the kernel function that is used to implement the kernel window centered on the Lth training training pattern. So hence this particular process guarantees that the first layer will be implementing the single window or the single person's window concept. So let's talk about the layer functions of the PNN. Say batch wise. So the summation layer computes the sum of the windows, persons windows of each class to obtain the required density values. The output layer shall have the neurons that will perform a comparison between the estimated probabilities at the point given as the pattern, the value corresponding to the maximum class probability provides the classification results, and hence, therefore, the output layer finally will implement the decision criteria. So, layer by layer, the class conditional probability calculated by the person's window kernels will be summing up the class conditional densities by the use of a voting that will decide the class decision between A and B, as shown by this particular layer. So a more simplified form that the Matlab will use, or Matlab will show. So between the input nodes and the hidden nodes, there will be a connectionist layer where, just like the previous feed-forward networks, a gradient descent-based training will take place, but the rest of the layers will be concerned with the calculation of the class conditional class probability density functions based on the person's window. So the PNN training is a fast procedure. So here we find that the PNN will just require localized parameter tuning, localized parameter variations. So this is in contrast with the classical training algorithms like the backpropagation, in which all the parameters are to be modified in each of the learning step. The procedure consists of considering a pattern sample for each new training pattern, varying its input weights so that they can coincide with the pattern itself. And the subsequent activation function is designed to implement the desired kernel function centered on the selected pattern. So while this pattern vector comes, that shall be scaled up by the weights in this particular layer. Now from this layer, while the scaling takes place, a class conditional probability by the person's window shall be calculated, and a voting will take place. That particular voting in favor of a class, say class 1, will lead to the decision making in favor of class 1. Same is the case for class 2. So the final decision regarding class 1 or class 2 will come in the last layer. So therefore, PNN's training in that way is quite fast compared to the previous cases where backpropagation is used and all the parameters are varied. here you find that just the localized parameters are tuned and changed. The summation layer has no tunable parameters. The weights in the output layer are given by the relative frequencies of patterns in the training set, so that their values need not be computed from the parameters, but from the numbers and the proportions linked with it. So therefore, the training is not an iterative one. That is a single shot process in a single pass through the training set. While the network goes, the decision is generated. So you need not run the recursion like the backpropagation repeatedly. Just a single shot through the sample space is sufficient to derive the class decisions. The main benefits that the PNN will provide is that the training is fast and an inherently parallel structure guaranteed to converge to an optimal classifier, since the size of the representative training set increases and the training samples can be added or removed by not considering extensive retraining. So you can add or you can remove the training samples by not considering very detailed retraining process. So now let's come to the recurrent neural networks. Recurrent neural networks are one more type of feed-forward network, but it has a feedback path too. This is a type of ANN where you find that that it has the capability to deal with time variation. So the recurrent neural network is common because of the fact that it has time tracking capability. So we shall speak about the recurrent neural network now. With these short points, a brief review of its capabilities, governing principles, types, the training mechanism, and the applications. Now, recurrent neural networks are linked with the dynamic processing of the patterns fed to a neural network. Now the dynamic characteristics the traditional ANN fails to demonstrate. So therefore, the recurrent neural network is required to deal with temporal variation, temporal processing. So all types of temporal processing when it comes to a neural network, that is called to be a dynamic neural network. The recurrent neural network is a dynamic neural network. So these will scale up the feed-forward network's capability to deal with dynamic situations by the use of a feedback loop. So this consideration tells us that the dynamic behavior in the traditional ANN can be provided by doing some structural variations. Now these structural variations can be done by the use of the time delays. They're in the feeding process or in the process loops, or recurrent neural networks can have certain recurrent connections that can be in form of feedbacks coming from the back end to the middle layers, from the middle layers to the front end. Sometimes you can also find that finite impulse response filters are used to generate or to provide the temporal or dynamic behavior in the recurrent networks. But these are not that common. Normally, time delays are used to generate the temporal behavior. So how you can visualize the time delays. So here is a case of time delay. Supposedly we have a feed of xn. So that particular feed can go in two ways. One directly, and second one through a delay block. Now these when go and do these when are considered together as part of an ANN, this will lead to temporal pre processing. This is normally done at the input layer. Now the second class of the RNNs that have the recurrent connections. That means to have the feedback from the back end to the middle layer, from the middle layer to the front end, or from the back end to the front end. Can be through these feedback paths. These feedback paths to also work like time delays, but they have greater capabilities. So the time delay networks do not have recurrent connections. So we need to remember that the RNNs are nonlinear dynamic networks. RNNs are used to classify into two distinct groups representing two distinct groups by the consideration of representation of time. These are continuous time systems and discrete time systems. So you can have two groups of RNN structures. These are continuous time systems and discrete time systems. Then a second property that you can link with the RNNs shall come from the representation of the signals. These can be, since we know that the signals can be real valued and quantized, therefore recurrent networks can be also real valued and quantized. A system can be real valued if it is implemented in the analog hardware, and all digital implementations are quantized, use quantized values, since values are stored in finite number of bits. So these two considerations will come while we design the RNN structure. Now we can group the RNN structures for fixed pattern memories and sequence mapping systems. So while the recurrent neural network is used to work with a fixed pattern that does not change in due consideration of time, then the recurrent behavior will be similar to the behavior shown by the multi-layer perceptron. So here there may not be much time variation, but minor time variation, and the response of the network or the behavior of the network will be similar to that shown by the multi-layer perceptron. And in the second case, the recurrent neural networks, the RNNs, can use a sequence mapping system to read the sequence and then link the responses to these sequences. So the sequence mapping is a capability, or is a domain where the recurrent structures are used very frequently. So if you have a time varying pattern that shows us variation in a long sequence of time, on a long range of time, you can have that to be a continuous time system. That in that particular case, the RNN structure will require a sequence mapping capability, or the RNN structure there should demonstrate a sequence mapping capability. So at each time slot, an output is generated, which depends on the previous value of the system and on the current sample feed. The entire output sequence generated in the due course of time and in the complete range of time is considered to be the result of the combination of the feedback and the forward computation. So there is a complete depiction of a recurrent structure. So we can see here there is a feedback coming here. This is coming through a tap delay line. Now in the first layer, in the front layer, we have the inputs coming. So they will go through a just like the multi-layer perceptron, they will go through a pattern feed layer scaled by a weight. Then there can be a bias value coming in that shall also be scaled up by a weight, and then go to the summation block. Now to this summation block, you see that there is a feedback path coming through a tap delay line. So this particular tap delay line will have a weight. That particular weight can change while you do the training. So this particular tap delay line will receive a feed from this point. This point is the output layer. So from there a feed comes. That particular feed goes through a tap delay line. It comes to the layer 1. From that same feed, from the layer 3, one more feed goes to the tap delay line, scaled up by a weight, and goes through the summation block in layer 2. Now at the end of the layer 1, we have a point there from where a local feed through a tap delay line scaled by a weight comes to the summation block. So here we see that there is a local recurrent structure, and then there is a global recurrent structure. The global recurrent structure feeds from the layer 3 to layer 1 and layer 2, while in the local case there is a feed from the end of the layer 1 to the front end of layer 1. So both these local and global feeds together give it a contextual or temporal processing capability. This part is very crucial, or this sort of a structure is very crucial in doing sequence mapping or in its use with time processing applications. So since we know that in case of sequence and signal and speech signal processing, time is a critical factor. Sequence and speech processing are time dependent phenomena. Therefore, to deal with time varying signals, you need these type of recurrent structures. One can be a local one, and one can be a global one. The local one will preserve the local context, will keep track of the local variations, while the global one will deal with the global time variations. Let's talk about the RNN types. There are 4 broad types. First one is the fully recurrent neural network. Then a second one is a simple recurrent neural network. And the third one is a partially recurrent network. Last one is a simple recurrent network. Now, in the fully recurrent neural network, you will find just like the previous block, there can be local and global feedback paths. So here there can be one more feedback path in the layer 2. Then there can be one more local feedback path in the layer 3. There can be a global feed coming from the end of the layer 3 to the front end of the layer 3. Then and the rest of the global feeds will remain the same. Means there will be recurrent structures, both local and the global type, for all the layers that will be forming the RNN structure. And in the case of the second one, the recurrent neural network, you may not have both local and the global recurrent behavior in all the layers. You may have a local recurrent behavior in the first layer. Then, in the case of the global recurrent behavior, the third layer may have a feedback path. So this one can be a recurrent neural structure, but not a fully recurrent neural network structure. So this one, since has one local recurrent topology and two global recurrent topologies, will represent a recurrent neural network structure that is a simplified form of the fully recurrent neural network. And in the case of the partial recurrent network, you will find that there might not be local recurrent structures. There may be just global recurrent structures, or there might be just only local recurrent structures. There might not be global recurrent structures. So these two variations shall be there in the case of the partially recurrent network structure. And in the simple recurrent network, you will have just one recurrent structure somewhere that might be there in layer 1, that might be in layer 2, or that might be in layer 3. Now, the RNN structures are quite frequently represented by the state space model. Since the state space model gives us a very clear view regarding its discrete time nonlinear behavior. So it's since the recurrent neural network is known for its discrete time nonlinear behavior, state space model permits us to show the role played by the pattern feed vector X, and there is a context vector U. So in case of the multi-layer networks, multi-layer perceptron networks that we had seen previously, there is no consideration, or there is no case of the state vector or the context vector U. Now this particular context vector U, and you might be here noticing the fact that both U and X will be showing a function form, and that takes the value small n. That particular small n represents time. So both the pattern vector and the context vector will show us a stark dependence on time. And then from the present pattern feed vector U and context vector pattern vector X and the context vector U, you will find the generation of the next sequence, that is the X of n plus 1. That will mean that will generate the next state of the vector, and use it for generation of the complete response of the system. So here there is a delay, and that particular signal going through the delay will generate a vector xn plus 1 that will be used for doing the processing and will be used for generating the response of the system. So that is a much more simplified representation by the use of the state space vectors that shows clearly in each layer the role played by the functions, the role played by the pattern and the context vectors. So here is a diagram of a fully recurrent network. So you might be here seeing clearly that that all the neurons will have feeds from the feedback and the feed forward paths. So when the neurons are receiving feeds from the feedback and the feed forward paths, all the neurons, then you get a fully recurrent neural network. So this is trained with a method called the real-time recurrent algorithm. So that is called the RTRA. So this particular RTRA will be used with the real-time recurrent neural network, where you find that all the neurons will receive both feed forward and feedback components. It's computationally quite demanding. One more such such structures where you can have that there is more number of feedback paths compared to the pattern feed numbers of neurons. So this is a fully recurrent neural network structure. Then you can have some variations of the fully recurrent neural network, where you will have a delayed feeds coming from the output layer. So here are the delayed feeds. Now this particular delayed feed will provide greater contextual processing capability. So when the time variation is quite significant, the time dependence of a particular signal is quite prominent or is of significance, then you can use these type of structures. So the delay paths can be there in the just prior to the feed, here in this feedback loop, or in this feed forward loop, or like this there in the output layer, where you can have the feeds, the delays, and those delays can come back and provide the feedback and the context generated. Just I said previously that in the case of the partially recurrent neural network, you might have lesser number of links. Those feedback links might be lesser. So and those feedback links might not be might not be following very stringent requirements. So you have a partially recurrent neural network structure generated. And there, in case of the simple recurrent network structure, you might have just one particular feed, one particular feeding type. So here it might come from the hidden layer to the context layer, and then the input layer going straight forward, the feedback coming to the context layer or the contextual layer. Both will be combining. So here we can find that the feedback requirement or temporal requirement is not that stringent, but just a minor temporal processing capability is required. In that case, simple recurrent neural networks are suitable. There are four training mechanisms. One is called the back propagation through time. Second one is called the real-time recurrent learning. And the third one is called the DEKF, or the decoupled extended Kalman filter learning. Then the fourth one is called the complex valued real-time recurrent learning. So these four types of training methods are linked with the recurrent neural network. Now, in the case of the real-time recurrent learning, we find that the weight variations or weight tunings are made in the synaptic links of a fully connected recurrent neural network in real time. That is, while the network continues to perform its signal processing function, you will find that weights are being tuned, weights are being varied. The network has two distinct layers: a concatenated input feedback layer and a processing layer of computation nodes. Correspondingly, the synaptic connections of the network are made up of feed-forward and feedback connections. So here is a depiction of the real-time recurrent learning. So if there are changes taking place, so a sensor here feeding data in real time, and a particular model is trying to learn that. So in that case, we need to have here a real-time recurrent learning. So here the mechanism shall be a supervised mechanism. So the supervised mechanism will be taking the samples in real-time form, and the data will come in real-time form, and the learning too will be taking place in real-time form. Then when you want to do some trajectory modeling or some trajectory tracking, in that case too, you need to use the real-time recurrent learning, and that too will also require the feed coming in real time. So this is how the real-time recurrent learning will be considered for real-time situations. Now, in backpropagation through time training, you find that the RNN will be just a variation of the standard backpropagation training. So we may see that to be derived by doing an unfolding of the temporal part that the network has into layered feed-forward network, a topology of which grows by one layer at each time of training. So that means supposedly you are doing a training of this particular layer F. So here there is a network. So while you have different training time slots, like say T1, T2, T3, T4, T5, T6. So this F can have different replicas at different time slots: T1, T2, T3, T4, T5. So at T1, that will take a different shape. At T2, that can take a different shape. At T3, that can take a different shape. So that means you are unfolding the networks, varied versions at different variations of time. So it learns, or there is a back propagation going on in the network structure at different slots of time, at different time counts. And when your time comes to an end, the last time where the network has a different structure, that particular network will be considered to be the latest version of the network trained by the backpropagation method. So this is the backpropagation through time training method. Now you can have you can have a backpropagation method, or a backpropagation through time method coming in form of a unidirectional backpropagation through time. So where you can find that the backpropagation uh, uh, through time is taking place in a unidirectional way. Say to begin with, the feed comes from top to bottom only. So from the top to bottom only. So the destruction caused by the forming. So these words or this type of sequence count will require a a feeding mechanism which will be a unidirectional type. So here you need to use a unidirectional feeding mechanism to keep count of the sequences coming to the network. Sometimes you need to know, you need to have a bidirectional back propagation through time training, where you need to keep count of multiple sequences coming at different time slots. So those can be from top to bottom, like this, top to bottom. And then you need to have more context generated. You need to make the network be fully confident with the variations taking place in the sequence feed. Then you can see that the training feed goes from the bottom to top. So both this top to bottom and the bottom to top mechanism means a backward and a forward directional feed uh, will take place or is used in doing the training, in doing the backpropagation through time training. These sort of mechanisms nowadays are very much popular in deep learning, and therefore recurrent structures are very stringent structures of deep learning network. So these particular methods are very pertinent for deep learning based sequence tracking or sequence prediction language translations. Then there is one more training method called the decoupled extended Kalman filter. Now, in this particular method, you shall find that the RNN is considered to be formed by a uh, number of Kalman filters coexisting in a decoupled form, not linked form, and each of the Kalman filters are trained separately, yet later on combined to generate the response. Now Kalman filter is a type of filter that has real time behavior. So its real time behavior makes it quite close in response to the RNN structures. Therefore, the RNN structures are considered to be constituted by the Kalman filters in the linked or decoupled form. They are trained separately and later on combined together. Then last one is the complex valued real-time recurrent learning, where you can find that the signals are broken up into two separate components. One is called one particular signal, or one particular signal feed might have a real valued one, and the second component can have an imaginary component. Both these two components are fed separately, and that way the network is trained. So you can find the in phase and the quadrature phase component of the signals are separated out and are fed to the network separately. Network trained that way, and finally the responses of the two separate networks are combined to generate the complex valued output response. Now we will find out where is the RNN used more more prominently or more frequently. The most common thing is that you can use the RNN for the IO behavior of a dynamic system. Then you can use it for the time series prediction, then sequence classification, feature extraction, and modeling a finite state machine. So let's talk about the time series prediction by the use of the RNN. So we have seen it just before in this case. So this is a case of a time series prediction where you can have a unidirectional or a bidirectional training or feed through which you can track the sequences, or you can have um, simplified network copies, and in the simplified copies of the network you can feed the sequence, and then each of the network will be generating the responses, and the topmost layer or the topmost network will generate a response and feed the next network. Second network will generate a response and feed the third network. Third network will generate a response. That way, you can have a time series prediction generated by the use of an RNN. So this is a very reliable means of doing time series prediction. This is quite useful for deployment with stock market, financial fluctuations, banking, weather prediction, so on and so forth. Then one more very pertinent use you can find with the RNN is to replicate the behavior or simulate a non-linear dynamic system. So now supposedly you have a non-linear dynamic system there, represented by the capital F. So this particular block F, this is a non-linear dynamic system. Now that particular non-linear dynamic system is fed by a sequence U, goes through W, reaches to this F. The F will be generating a response, and that particular response is fed through a delay, comes back here, and in this particular W, you have the feedback component, small xn. Now un and this xn together will be generating or keeping track of the context. Context will keep track of the variations that shall be there in the network. Then quite frequently we see that the recurrent structures are used or are preferred for sequence classification. Now, how to do the sequence classification? We can see here that there can be a few number of recurrent structures grouped, and the recurrent structures, as we have seen just beforehand while doing a time series prediction, each of the previous blocks feeds to the subsequent block, towards the right, or in below, or placed below. So they will feed from left to right, or will feed from top to bottom. Now that way, the first block or the preceding block, laterally and vertically, will keep the context, learn the context, and pass it to the subsequent block. So that way, it can learn to classify sequences. Then one more case is that quite frequently, mainly in the case of the speech processing, speech processing, since is a very significant part of man-machine communication. Therefore, we need to have very delicate features captured from the speaker's tones. So you can find that are that the recurrent structures are quite well versed in capturing the time dependent features. So here you have a high level feature representation, a frame level feature extraction taking place. Then you can find you can simultaneously find that a utterance level classification of the features can be also captured. So you can have here one recurrent neural network, though we are here showing to be a deep neural network. That can be also a recurrent neural network. Same way, there can be a recurrent neural network too that will give us the most or a very precise representation of user level speech features. Now we come to the self organizing map, the SOM, self organizing map is a network that will be dependent primarily on the unsupervised paradigm, that is based on unsupervised learning. So here, therefore, we will be briefly reviewing the supervised and unsupervised training. We will be speaking about how Kohonen spoke about or derived the SOM. We will be speaking about the competitive learning, and we shall be roughly covering the network structure of the self-organizing map. Now, we know we have talked about the unsupervised learning in some detail. Unsupervised learning is a type of learning where there is no reference, there is no labeling, there is no prior labeling done. So there is no prior know-how. So you can use those patterns, and those unlabeled, or you can do a training with no prior reference. So there can be a few blocks. One block can be to do a clustering, where we find that the pattern groups are formed based on similarity. Then you have a vector quantization. That means you will fully divide up S, that is a sample supposedly, into small sets of regions defined by a codebook vector, set of codebook vectors. That too also helps you to form the cluster, supposedly it's P. Then you can do a feature selection. That means you will be reducing the dimensionality of the sample space S by removing the unimportant features. That is, those features that you find are not suitable for doing the clustering, you will be removing them. So unsupervised classification learning is based on the clustering of the sample feed. You do not have any prior knowledge. Then here is a depiction of the unsupervised learning. So you have the raw data coming in. You will try to find out some interpretation or meaning out of that raw data. You will have an algorithm which will help in processing the raw data. and then you will be combining these steps and then segmenting them into separate clusters or separate classes. Means there will be no prior reference, there will be no label data. So you will just try to do a grouping by the on the basis of similarity, on the basis of commonality between the samples. Now the philosophy is that Kohonen called it to be a winners take all network. Since Kohonen first proposed SOM, and Kohonen therefore called it to be the winners take all network. So that means you will have a group of uh, neurons. Those group of neurons will have weights. Those are randomly given. When a sequence of samples come in, x1, x2, dot dot xn. Now these particular sample values will be compared with the weights linked with a particular neuron. Now the weights linked to the neuron that will have the closest difference between the sample values and the weight will get the sample value in that first run. This particular mechanism will go on by doing a sort. Supposedly, the third neuron in the first run, in the first cycle, has a weight that has the closest value with sample one. So then the third neuron will get the first sample value. Same way, if now in the second cycle you have the second neuron possessing a very closeness to the fifth sample due to the weight link with the second neuron now will get the fifth value, and then a sorting will take place. So this way, a closest match between the sample fed and the weights connected to the neurons lead to grouping of the samples with the neurons, and that way the topology is built up. Now, this particular topology at some point of time will have a number of samples coming and becoming closer. This particular closeness of the samples, thus grouped, will form a cluster center. Around that cluster center, the rest of the samples will group and form a cluster. This particular grouping leads to a clustering, and that way classification is generated. So this is the things I said. So here the weight readjustment during the training will follow a gradient descent method. So the three steps, you will take a weight W that is defined by this WR plus this step size X minus the WR, the weight, the random weight, and if you have a winner neuron R, so that particular weight will be linked with that winner neuron. You can normalize the weight value and then reorder and regroup. Then finally we have that this particular gradient descent based weight tuning will go on simultaneously to vary the weights of all the network, and that will lead to the formation of a network topology and will form the SOM neighborhood. So here you will find that this way the grouping will start to take place around the weight W1, W2, W3. So this is called, this was proposed by Kohonen, and hence this particular form of learning is known as Kohonen learning 2, and is the basis of the unsupervised neural networks. So SOM is the organizing map is the best case of the unsupervised neural network. You have to learn a categorization of the input space. Then you will find that neurons are connected to a 1D or a 2D lattice structure. Each neuron represents a point in the n-dimensional pattern space defined by n weights. During the training, the neurons just go around to try and fit into the data, and changing the location of one neuron in the data space will force to reorganize the locations of its neighbors via the lattice connection. So you will find that the neuron may move around through the data space and do a regrouping, a reorganization of the network structure. So we can see it from this particular diagram. So while you have a pattern vector coming in, so if with this particular pattern vector, the first sample, so you take the first sample, then you find that the third one is the winner. So this first sample will go to the third neuron there in the neighborhood. So this will form the neighborhood. So and then the whole of the neighborhood will form the grid. Now this particular neuron will now move to first place, and then the grid will change its structure. There shall be a regrouping, and finally that particular regrouping will take a shape of this type. So here we find the cluster map developing, the yellow map, the yellow neurons grouped in one particular form. Then you have the gray ones, then you have the blue ones, one more time the gray ones, like that. This whole build up of the cluster and the map will take place from this regrouping of the neurons by following a winner take all philosophy. So that's the summary of what we said. That is as proposed by Kohonen. So this two-dimensional neighborhood or map you need to take and first randomize it, present the training data to the map, and let the cells on the map compete to win in some way. You may take the Euclidean distance to be a measure quantity, and then stimulate the winner and some friends to form a neighborhood. Now do this a bunch of times, so you can repeat it multiple times, and then the result shall be a two-dimensional weight map, and that particular weight map will represent the SOMS topology, and the neurons forming the clusters will lead to the completion of the classification. So here is the SOMS two-dimensional map. First, you will be randomizing it. So once you have the map randomized, the two-dimensional map, you will feed in the weights. Once you feed the weights, the neuron that will have the closest match with the samples will take the value. So when you present the training data to the map, let the cells on the map compete to win some way. So this particular philosophy will go on, and the winner neurons will take part in forming the neighborhood and the grid. So n-dimensional training vector that will lead to the formation of a n-dimensional neighborhood, and that will help in doing or building the clusters. So in a bigger space, you can find the node that has one can lie in the center also, or in the sides. So around that center node, you will find that the building of the neighborhood will take place. So this particular building of the green colored nodes will form a cluster, or that may represent a reduction of the sample space, or a dimensionality reduction can be said to be taking place in this particular form. So so if you do that for some samples representing geographical physical quantities, you find that in that neighborhood, or in that clustering, you can have representations for the water, you can have representations for the cloud, you can have representations for the base soil or the rock, you can have representations for the vegetation, so on and so forth. So this will lead to the formation of clusters representing specific classes. So how this clustering leads to classification, this particular slide shows it clearly. So once the training is finally finished, the clustering is taking place, then you can do the classification. So so you can have the class level pre-assigned to the groups, create a visually closed map, and then you can find out the differences or the and distortions that might have taken place while you have created the cluster maps. This is called the comparative learning. Now, this is called the Kohonen style of network training, known as the comparative learning. And this is due to the fact that during a single training epoch, the cell with closest distance to the presented training vector vector can be considered to be the winner, and is thought to have successfully competed for the honor, and hence the concept of comparative learning. There can be two types of comparative learning. One is hard and the second one is soft. In the hard comparative learning, you will have a winner-take-all type of philosophy. The winning neuron is the one that will receive the training response. And the soft learning, you can share your neighbors. So in the soft comparative learning, just like the cat sharing the space with the kitten, with the kittens, you can find that the neighborhood can be shared with the neighbor neurons. So there is a shared space too. So how the two-dimensional Kohonen map can be built from the input layer. So the whole thing can be summarized like you can have have the weights randomized. Then you can draw a sample. You can do a sampling and draw a sample and present it to the network. You find a similarity match. That particular similarity match will decide the neuron that will win, and if it wins, it will take the vector, and that particular weight will have the sample from the vector. This particular process will go on. So then weights will be varied by considering a gradient descent, and in the time the neighborhood function will get smaller, and then you will have the neurons providing a good approximation of the input space and corresponding response generated. Now, similarity, what are the similarity factors, measures that you can use here? The most commonly used one is the Euclidean distance. Then there are some more metrics like the uh, Minkowski's metric family, Tanimoto distance, Chebyshev distance, fractal distance, the homegrown distance metrics, and the text-specific similarity matrices. So you can find that the properties that you need to guarantee, or you have a guarantee, is that you will have a topological preservation. Cohen's are topology preserving networks. So this means that if training signals are close to each other in the real world, they will be close to each of them in a trained Cohen sum. The topology representing networks are biologically justified. These renitropical mapping between the retina and the cortex, and you have the somatosensory mapping, just like the ones you have in the brain, and in the case of the linkage between the retina and the cortex, you have the topology representing networks. Therefore, these Cohen sums are very significant developments in the neurocomputing domain. Okay, same thing ultimately. So we can here summarize. We have the PNN to be a feed-forward NN that takes a single step training to perform pattern recognition. Its core part is formed by Gaussian kernels linked with the connectionist weights that will use that will be used for doing the pattern feeds. Then RNN is a network that has both the feed forward and the feedback connections. Feedbacks can be global or local. These feedbacks are quite beneficial for tracking time dependent variations. Then the SOM is a topology oriented network that will use an unsupervised paradigm to train and perform pattern recognition. So the references, the most comprehensive is that neural network book by Simon Aiken. So before I end, I would like to request you all to raise questions. So I think all the parts are quite clear to you all. I shall be sharing the slides with Dr. Kaplan, so you can see them. In the next class, I shall be speaking about how to train these networks in the in the MATLAB domain, and how you can do the programming part in the MATLAB. MATLAB has several built-in functions, and the visualization is quite good. So I shall show that, and in the subsequent class I will be further talking about the dynamic neural network structures. So next Tuesday we shall learn how to or be familiar with the different techniques that are there in MATLAB, through which these type of networks can be designed, and how to see the contents, or how to use the neural network toolbox that is there in the MATLAB. So that is quite good to learn. So with these, I thank you all and hope that the session was beneficial to you all. Thank you.